For the last half-century, space travel has been dominated by rockets. But before advancements in rocket technology allowed us to use them to go to space, there was always a thought that guns would be used to take people to space. In modern times, this is largely unfounded, but we can still look at the mathematics that would be involved in building a gun to take someone to space, what the dimensions of this gun would be, the times involved, the speed of the projectile, etc. So, to start off, we're going to look at the equations that we need. This equation we need to find the orbit, the velocity that we need to, our projectile needs to be to orbit. We have kinematics equations here for finding the times and velocities. We have the kinetic energy equation for finding the kinetic energy. And this new equation, which where A stands for the acceleration of the projectile while it is launched from the cannon, velocity E, which is the exit velocity of the projectile that leaves the gun, and L, which is the length of the gun. We're also going to be using the Pythagorean theorem. Now there are a number of given values that we need, including G, our gravitational constant, which is 6.67 times 10 to the negative 11. Need that for our orbit, as well as MP, which is the mass of the planet, RE, which is the radius of the planet, G, which is the force of gravity, or the acceleration due to gravity, rather, LEO, which stands for low Earth orbit, which is our goal for our projectile to reach, which is 160 kilometers. We're also going to be looking at human G tolerance, which it depends how you're sitting and whatnot, and the health of the individual, but we'll make the assumption that it's 35 Gs, which of course times the acceleration due to gravity is going to be 343 meters per second squared. We're also going to be making the assumption during this that that it's perfect weather, our gun won't melt, and that we're in an absolute vacuum. The mass of our projectile is going to be 21,250 kilograms. This is the mass of NASA's Orion spacecraft. And that's all we need to get started. So let's look at the x-axis of motion first. We need a certain velocity in the x-axis, otherwise our projectile is going to drop out of orbit. So we take our equation for finding the orbital velocity, plug in our two constants, add the distance to low Earth orbit plus the radius of the Earth. We end up with 7,809.5 meters a second. Now let's look at the y-axis. Our y-axis isn't quite that simple. It needs to have a certain speed that it eventually ends up at 0 when we're at the proper distance. And that distance is our orbit. So we plug in 0 for our velocity final, because we don't want it to be moving vertically once we get to our perfect distance. We are going to plug in our acceleration as the acceleration due to Earth's gravity, negative 9.8, as well as our distance, which is the distance to low Earth orbit. From that, we're going to get 1,770.9 meters a second. Now, with this, we can also figure out the flight time of our projectile, the time from when it leaves the cannon to when it's in orbit. For that, we're going to be looking at the VF equals VI plus AT equation. Plug in velocity final 0 minus the velocity we found that we need in the y-axis, divided by our acceleration, which is going to give us 180.7 seconds, which is almost exactly 3 minutes. Now, with both the x and y components, we can create a right triangle and find both the angle and the total velocity of our projectile as it leaves the gun. So we've made a triangle here with our components. We can use the Pythagorean theorem to figure out that our velocity needs to be 8,007.8 meters a second. We can also use trigonometry to figure out what angle our gun needs to be pointed at, which is tan opposite over adjacent. We're going to end up with 12.8 degrees. So let's write these numbers down here on our gun. The time is going to be 180.7 seconds. So let's move on to the gun length. For the gun length, we're going to use our new equation, which is A equals VE squared over 2L. Move this to solve for 2L. We're going to plug in our the velocity we found from here, which is 8,007.8 meters per second. That's going to be over A, which is going to be our parameter, our maximum acceleration we're going to have, which is going to be the human G tolerance, 343 meters per second squared, our assumed human G tolerance. That is going to give us a length of 93,476.5 meters, which is about 93.5 kilometers, which is very, very, very big. Now we can find the launch time, that is the time our projectile is in the cannon, using this kinematics equation once again. Vf equals Vi plus At. Velocity final is going to be our speed when the projectile leaves the gun. Our initial velocity, we're assuming that this projectile is starting at rest at the bottom of the gun. So we'll set that as 0 over our acceleration, which is once again going to be the human G tolerance. This is going to give us 23.3 seconds of time in the gun. Let's write these down again. Now, our kinetic energy. We're going to use our kinetic energy equation. We're going to plug in our mass, which is the mass of the Orion spacecraft, which is 21,250 kilograms. Multiply that by our velocity, so we'll be finding the kinetic energy of the projectile once it leaves the gun, our velocity, our exit velocity here. And that gives us 6.8 times 10 to the power of 11 joules, which is a lot. So, in summary, let's look at all of our dimensions and energies we've found for this gun. It's going to be 93.5 kilometers long. The exit velocity of our projectile is going to be 8,007.8 meters per second. The time from the moment the projectile leaves the barrel of the gun to low Earth orbit is going to be 180.7 seconds. The time that it takes a projectile from starting at rest at the bottom of the gun to leave is 23.3 seconds. Our gun will be tilted at 12.8 degrees, and the kinetic energy of our projectile when it leaves the gun is going to be 6.8 times 10 to the power of 11 joules.